Um, yep. So thanks for the introduction. I'm Dan. So I work in Diamond's data analysis group. I'm in the team that focuses on eBIC software needs. So that's kind of including all kinds of installation of various pieces of software at eBIC and support for the automated processing pipelines that we have. I've just put that on there because I'm going to talk about some stuff that was partially funded by a EU Horizon fragment screen project. So the talk is going to be in kind of two parts. The first part will be some more general updates about eBIC, so new and upcoming experimental workflows for the user program, and some updates to the automated processing pipelines that we run. If people were here yesterday for the BCI user meeting, some of that, well, that will be very familiar from Dave Farmer's talk. And then in the second part, I will go on to talk slightly more in depth about a particular project, which is the part that was funded by the fragment screen Horizon money, which is to look at how we can move towards automating SPA acquisition more. So by that, I mean automating the steps where you make selections of grid regions that you're going to image at high magnification, and also get some feedback from the processing results to help guide that acquisition as it happens. Okay, so the general eBIC updates. So the big one is that there's a waffle milling workflow, which can now be requested via rapid or bag access routes from the eBIC. If you want more information about that, Ailish is here somewhere. She's talking later and has a poster as well. So you can find Ailish. Then sticking with the milling side, there's going to be a phased rollout of some of the adaptive milling workflows being developed at Rosalind Franklin Institute across the road. So Tom Fish has a talk later today, I think, and a poster about that. And then in May, there's going to be the announcement of a commissioning call for cryo lift out workflows. Then on to some updates on the automated processing side. So for single particle, so within the data visualization web platform that we have, Pato, which Agnel mentioned, every atlas image that you take gets displayed in there, so you can see all of the atlases, even if you don't actually take data on them, and you can see which slot in the cassette they were and things like that. On that atlas view page, once you start doing data collection, you can click on individual grid squares, see the grid square mag images, and then on those grid square mag images, we can apply a heat map coming from the automated process data, so you can see TTF max resolution, particle count in those different holes as a heat map, to get an idea of where the highest quality data is coming from. Pipeline, if it works well enough with the data set, we'll try and do some automatic refinement still at bin 2, but can get to, on very easy samples, can get to sort of 3.5 kind of angstrom. And then that will also run an automated symmetry estimation to see if it can apply a symmetry to improve that. We display some information now about the angular distribution from the refinement of different particles. So these kinds of 2D projection plots that we're also showing appearing now in Doppio. And we calculate the cryo-EF angular efficiency score and display that. And then to link back to another thing that Agnel was talking about, these EMDB MMSIF file deposition files. So in Pato, there's a little download tab where you can download. There's two options at the moment. One's a PDF report, which just gives you a summary of the data collection. And then the other is a MMSIF file, which contains some instrument and acquisition information that's that you can then, or you can either just directly use that or import it into Doppio, and then have also Doppio add all of the processing information to that MMSIF file, and then partially populate EMDB deposition. Kyle is going to talk about that in more detail next. For tomography, we have the same kind of atlas view. So there's an atlas view. You can see the positions of search maps on the atlas. It's not very clear on that one because they're very small. And then positions of individual tomogram acquisitions on the search map. And there's some stuff's gone in to better help visualize alignment quality. So this kind of thing with the colored squares is showing how much the field of view is shifting in each tilt. And some more segmentation stuff has gone in using membrane seg for the membranes and easy mode for some other stuff. So like ribosomes and microtubules on that image there. And there's I think there's a talk about easy mode, later today as well. So yes, now moving on to this kind of a project to try and see how we can move towards automating SPA more completely. I've got a list there of people so Kyle, who is actually giving the next talk now at the EMDB, kind of started this project off while he was at eBIC. Jaehoon from SDFC's AI for Science group has done a lot of machine learning stuff with us for this project. I won't actually go into much detail about that for time reasons and hopefully to keep things kind of cleaner, but he helped a lot with that. Val and Stephen have worked on the software side, and Pete and Teresa have made some samples for us in some of the data that I'll be showing later on, and done the data collections for us. So to briefly talk about motivation for why we want to more completely automate the SPA acquisition pipeline. The ultimate goal would be, it's kind of obvious what the ultimate goal would be, is you just load the cassette into the microscope and then the microscope takes data. You don't have to interact with it in any way. So for very high throughput use cases, that would maybe be what you want to do. If you've done a lot of work on optimizing your sample preparation of a specific sample, and you know you're going to get a bunch of good grids that you just put in the microscope, and you need to churn through grids as fast as possible for things like fragment screening use cases. You would ideally want a fully automated system for that. But obviously that won't be every use case. So we want the results of this to also be useful to someone who is going through doing some manual selection. Maybe it makes some suggestions to them that are useful, or it records information, like more rich information about the acquisition, which then can inform future decisions if you're kind of going to be imaging on similar grids. And then these plots that I'm showing are little just screen grabs from Pato for a couple of data collections. So you can see patches in here that I've highlighted. So one is the top one's the CTF max resolution. You can see areas where it clearly jumps and then comes back down. So these are kind of like you're going through a bad region, or maybe a bad grid square in particular relative to the rest of the data set. Or in the particle count one, there's some very clear gaps there where the particle count just drops off a cliff. So you're probably going through some very poor region of the grid, either empty holes or obscured. So you want to be able to respond to those kinds of, this could be happening at 3 a.m. You don't really want to be collecting this data, so you want to be able to respond to that. And then one of the things that we wanted was also a methodology to apply the lessons learned from previous collections, by which I mean if you've done a data collection on a grid with a particular sample, and you're going to be looking at another grid with very similar sample preparation conditions, same or very similar sample, you want to be able to basically directly take some of the information that you've got from like a screening stage or something like that, and apply that to future data collection. So some of the challenges in doing this, I just have some of these that are like very rough, quick calculations that I'll show in a second on a couple of data sets. What you need to be able to do is make a decent prediction of quality outcome however you're measuring that, based on lower magnification images. So in this SPA case, by lower magnification images, I'm really talking about sort of grid square mag if you want to actually maintain high throughput, because you're not going to get a foil hole mag image for every foil hole. It would take too long. So finding strong correlations between things that are visible at that magnification and measurable processing outcomes is pretty difficult. I'll show some stuff in a bit. There's also a kind of, if you're trying to do this as the data is being acquired, there's a time constraint, which comes from if you're feeding back quality metrics from the processing to guide the acquisition, that needs to be happening quickly. You can't sit and wait 5 hours for some refinement to run to tell you something about the data. So at least initially, you'll be using some fairly early stage processing metrics. You also want to be able to adapt very quickly to the data collection. So waiting for thousands of images to be collected before you make further decisions on the acquisition is too long. You're then quite far into your acquisition. And what exactly constitutes a good value for a given metric will vary across data sets. So these are some basic correlation coefficient calculations on a couple of data sets. So the blue thing is one data set and the orange table is another data set. What I have in here is, so the total motion from motion correction, CTF max res, and number of pics from Cryolo. And then as a proxy for something visible at low mag, I'm just at the moment using, for this crude calculation, cutting out the foil hole from the grid square mag image and then taking the average pixel value. So that tells you something about the ice thickness, basically. So that's something that is definitely visible at that scale. And then you calculate, you see if you get any correlation. So in one data set, I mean, 0.87 isn't actually a great correlation coefficient, but the data is very noisy. So there is something there where that kind of intensity score is correlating with the motion, less on the CTF max res, and some of this is because these are intentionally unclean data sets. They include a bunch of empty holes and things like that, but all of this like ruins your correlations, and that's the kind of thing you have to be thinking about if you're not going to have any user input. The kind of the holes with no ice in them and things like that are going to be in the set of things that you're considering. So there's some correlation in that data set, but it kind of just completely falls off for the number of pics. And then in another data set, there's just no correlation between anything. So you're working in this kind of environment where you're getting weak correlations that you're trying to make these predictions based on, noisy correlations, and there's variation across different data sets. I basically just compiled a list of things here that work in this kind of general area, different approaches that have been taken. So there's things like Ptolemy, which is part of the kind of Legion acquisition framework. That gives grid square and foil hole classifiers. So these were classifiers trained on data sets that are collated by basically just saying anything that a user selected to image is considered good, and anything a user didn't select is considered bad. So that's a kind of pre-trained approach. We'll get rid of very bad stuff. Then in terms of actually trying to find a path through, an efficient path through the grid for collection, there's cryo-RL, which is a reinforcement learning approach, which in the paper was driven by predictions of the foil hole of whatever the CTF max res is, and then try and find the most efficient path through the grid to get the best CTF max res earliest. But you could in principle use other metrics there. Smart scope, which is a more general kind of thing, like a wrapper for a sort of wrapper for serial EM, which has some automated workflow tools in it, similar to Ptolemy. I think you can also actually use Ptolemy in Smart Scope. And then there are Thermo Fisher Thermo Fisher things inside of EPU, so smart EPU, which will do some quality assessment of regions, so quality assessment of squares and holes, and give you some tools to tell you which foil holes are like which other foil holes, so similarity measurement on the squares and holes. And there's also some level of integration with Spot Live in that. So now I'm going to talk about what we're looking at, what the kind of framework that we've been using to try this out, to try and actually progress this more towards actually being able to offer some automated SPA. So a key thing for us is flexibility. I don't think you'll be able to train a single model that is just pre-trained and just works for every data set. The variation is too great. And you might want to consider multiple different models, either machine learning things or things that are just trying to make predictions based on what the ice thickness values you see, or physical distribution on the grid or something like that. So we wanted a framework that would allow us to combine information from multiple different models. And then the other thing is the metric that you're using to assess how your model is performing. We didn't want a single metric, because if you just pick something like the CTF max res, for example, and then you're optimizing for that, there might be a trade-off between CTF max res and the number of picks you're getting, or various other things. If you have data sets with preferred orientation, you might care more about whether you're seeing a certain view or not. So we ended up with this kind of idea of a model metric matrix, which is what this sort of cartoon is showing here. So this would be like a weight matrix. So what you have is you have various models making predictions. You're calculating various metrics as you process. You then assess using a kind of Bayesian updating framework how each model is performing versus each metric, compose a weight matrix over that whole thing, and then kind of roll that all down into a single score that you're giving to each foil hole, basically. And then go and collect in regions with the highest score density. You don't want to be pinging about all over the place. And then constantly be updating that process. So that's the sort of general framework we're looking at. So in terms of how you would get to a completely automated workflow, you initially need to take Atlas images of all the grids. That's fine. Then for each Atlas image, make an assessment of the grid square quality across the grid. So this is like a basic pre-trained, just a quick how much complete crap is there on there? Are there a good number of fairly large squares that seem uncontaminated? And then you can kind of make an assessment across all of the grids, decide which one you're going to image first, and then make some suggestions for squares you might want to look at, which will incorporate information both about the quality of the square, so you only really want to be looking at squares that you think are of decent quality, and also getting some variation in the squares, because you might have, and in what we run later on, you do have models that try and tune themselves to the data set. So you want to, based on different groupings of squares and foil holes, so you want to kind of sample that distribution a little bit to get some feedback quickly. So you'd suggest doing like a quick early data collection to get some of that feedback going. You would then move to these squares, do grid square mag images, analyze at the foil hole level. So this image is of the squares. The top one is a prediction from a neural network, and then the bottom is the actual CTF max res value heat map from Pato. And then once you've done that assessment, you do this early data collection, feed that back, then go back to Atlas Mag, decide on a set of squares, queue a load of stuff up, and then as you collect, constantly update the predictions, shifting the acquisition ordering, And then at some point you have a stopping condition that stops you on that grid. So that could be time, number of images, or if you're seeing sort of strong quality drop off according to the metrics. This is just that workflow on a slide where I've then highlighted individual steps that if you want this to be a fully complete automated process would require direct programmatic interaction with the microscope to do this thing. So automating the kind of Atlas image taking processes, EPU can do that. But then once you have the Atlas mag images, you would need to load whatever grid you want to collect on. You'd then need to tell it to collect those grid square mag images and have it just do it. Then you can assess those. You can queue various things up, and then for the feedback, you're obviously going to need something that tells the microscope without user intervention what it's going to acquire next. Right, so I've got a few quick slides on attempts at validating the framework. It's quite because of this kind of same problem of everything's very noisy. You're looking at multiple metrics at once. Things tend not to correlate very well. Actually coming up with decent validation scores is a little bit of a tricky problem. And one of the other things is you don't want to just validate on a data set that a human has already chosen the positions of, because you're getting a biased data set. If you're trying to fully automate, you're going to see the whole grid, and you need to check that that your system wouldn't like drive to some crazy area of the grid. So in order to do some validation checks, we collected a few very complete data sets. So where we were collecting on the majority of the squares on the grid and in every hole of each of those squares, doing single shot per hole to get the throughput up. And then we kind of effectively have like a data set that's run through the processing pipeline. We have the metrics that would be returned for each of the micrographs we have in the data set, and then you can kind of iterate against that. You have you have these sort of complete data sets that you can just feed through the system and see how you perform. In the next couple of slides, there's some plots with some lines on them. The important thing is that the area under the curve is effectively the metric for how well it's performing. So if the area under the curve is bigger, it's doing better than another line. So in the full data set, I'm only showing the first 5,000 micrographs of these data sets, so you don't see this, but in the full data set, every line that you see would start at 0 and then go to some value, and every line would go from the same start point to the same end point with different paths, and the area under the curve is what's important. So this is a so these are like, there's a ribosome, an epiferritin, and a beta-gal data set. The green squares on here are squares that were collected, and every hole in each of those squares was collected. So the plot, these are the lines I was talking about. This top red one is what happens if ahead of time, because I know all the returned metric values for this data set, I can basically run through the system, giving it all of that information. So it knows which are the best areas, and then makes decisions based on that. The green line is basically if you do that process, but you don't give it that information. So it's trying to update as it goes along. And then the orange thing is it's the average value of a bunch of random trajectories through the time series. So in this case, you see the green and red lines are quite close to each other. You're far away from the random line, which is where you want to be. So decent performance here. This one goes a bit weird because the thing actually overtakes the optimized version, which is because of pretty sure it's because of a quirk of how I've actually constructed that metric. It's an imperfect construction, but that's the key there, is that the performance is like effectively within range of that optimized line that you're adding for. And then I've got a data set that doesn't perform so well, which is actually the data set from before, where just nothing correlated with anything. So you see here, it's doing it's doing badly. It's on the random line, and then it kind of takes a little bit of an uptick as it learns something about the data set. But it's struggling to learn something here because none of the reported processing metrics are correlating very well with anything visible at low mag. These are just some screenshots from kind of working on a front-end development to visualize some of this data. So this thing is the atlas with some, on the left-hand side, some quality predictions from one model, and then the kind of the colorful plot to the right of that is a latent space representation of all of the squares in that grid. So this is what we're using to decide if two grids are similar to each other. Just embed into a latent space, and their relative positions in the latent space tell you how similar the squares are, and you can cluster them and make decisions based on clusters of squares or holes. Then there's this is the kind of matrix thing that I was talking about. So this is at the end of a run where I've put, I think, 10,000 micrographs through it, and the system has basically decided that the best performing, so Y axis is four different models, X is 3 different metrics, the total motion, CTF max res, and number of particles, and it's picked out one particular model performing best for CTF max res and number of particles, a different model performing best for motion correction, and then some quality distribution plots across holes in a square. And then this plot is the time series of the micrograph. This is the value of the CTF max res, and the color is the cluster. So like this latent space clustering, but for the foil hole level rather than the grid square level. This particular sample was quite homogeneous. There's a lot of holes that look the same, which is this light blue color. There are you see these odd ones, like little purple and orange ones that you don't collect much of because they perform very badly. They're probably damaged or obscured in some way. And then there's this kind of green set, which is a slightly thicker ice. And you can see it kind of separates out slightly from the bulk of the rest of it. Very briefly so that's a kind of a system that can run. You feed it micrographs, processing happens, the processing feeds back to the prediction weighting system, and then it produces basically an acquisition order. Then the thing you have to do is actually interface with the microscope. So there's a couple of options we're looking at for this, and we're aiming to support both in some way. One is EPU has a way of making suggestions and skipping areas through a service that you ping, and the other is just going direct to Serial-EM, which gives you a bit more control. It solves problems like at the moment EPU won't let you take a grid square mag image like programmatically, for example. So that would be more complete. And then I'll just throw up other stuff on things from DLS, eBIC. So Eilish and Christian Orr are giving a talk later today, and then this is all of the posters from people from eBIC.